Hello everybody, this is Duminder and I'll be delivering FPC today. So usually I wait for 5 minutes, right? So let's start the lecture in a couple of minutes, right? In 2 minutes we'll start. Okay, this is Duminder again and welcome to the module. So before starting, I'd like to get some feedback whether you can hear me well. Can anyone let me know?
So loud and clear.
Okay, thank you very much. Right. I can see there are like 25 participants, 27, and I think there should be more. Okay, anyway, we'll start, right? So that this can join. So let me share my screen with you now. Okay, can you see my screen now? Anyone? Okay, thank you. Right. So I'm sure that you have received this communication from Mr. Shanaka, the welcome message, right? So here you can see that the assessment schedule, right? So now you are attending this session, right? And I'm Dominder, right? So you can see here that fundamentals of power conversion is a module fully based on what type of assessment on the evaluation criteria. So it will be fully coursework based, right? So there's no exam, right? So in this module, so then you are going to be evaluated based on a journal that you write and a final report that you write. So you can see the weight, the marks weight allocated for each of the assessment components, 60 and 40. right? And even the submission dates are set, right? So then everything is set and ready. So now it's basically the things that you learn and how you basically achieve your learning outcomes, right? And I'm here to help and guide you, right? So from today onwards, I'll be delivering this module, and we should thank Mr. Pradeepan. Unavoidably, last week I couldn't actually take up this module. So he has given you a good introduction to fundamentals of power conversion, so we should thank him. Right. So let us move on to the actual delivery. So I'm sure that Mr. Pradeepan finished the introductory session, right? Uh, but still, if you have any doubts, right, in terms of the introductory concepts of power electronics, fundamentals. So if you have any doubts, of course, I'm more than happy to clear anything, right? So anyone uh, who couldn't understand any concepts or anything related to that introductory session, I'm sure everything was very clear, right? Uh, anything that you want to know? So if not, we can go ahead with the next chapter. And to tell you a bit about me, so I'm full-time at Scott, right? And so I'm one of the EEE program managers, right? And I'm the module leader of this module. And in terms of my experience, so I have been lecturing for over 15 years now, right? So then I know you uh, because I have been an undergraduate once, right? And I've been teaching you, right? So it's okay. So if you have any doubts, so I know that you have completed your higher diploma courses, right? And you are partially, you know, eligible to join this top up. I mean, yeah, so you are in the level 6 now, right? So you have completed your level 4 and level 5 studies. So then you have some background, right? So that we can go ahead with level 6, this level 6 module, right? Right, so I don't see, at the same time, I want you to, you know, turn off your camera, right? And keep your microphone muted always, unless you have any questions, right? Any doubts? Of course, you can raise your voice, right? Please keep your cameras turned off, right? And also microphones are muted, right? Unless you have any doubts. Of course, you can interrupt me, right, anytime. So you can raise your voice if you have any doubts, right? I'm okay. I'm happy to help you, right? Or answer. Uh, right. There's one question here, engineering mathematics, right? So fine, right? Okay. So let me open that slideshow. Okay, so this is chapter 2, right? So in this chapter, the expectation is basically, so this is not, you know, anything related to power conversion, right? But this is simply to make sure that you have the background knowledge. Of course, I'm sure you must have gone through these concepts, because this is not level 6, mostly not level 6, you know, content, right? But of course, you may have forgotten certain, you know, parts of this aspects, it's okay, right? So of course, why we are covering this chapter before starting off with the concepts of power conversion is basically, so this is going to be the tool set, right? In analyzing, in designing, in testing, and when in evaluating your power converters that you are going to design later on, right? Even your coursework is based on design and evaluation of some power converters, right? So it's based on basically 4 labs that you do, right? And this module should be very interesting because it's not just theoretical, right? So it's practical, right? So you'll be learning certain concepts and you'll be designing your circuits, you'll be, implementing them, of course, on simulation and also on, component level in a laboratory, right? So then, yeah, so this should be interesting. It's not just theoretical, right? It's a practical module, right? Uh, okay, so yes, so this is not BSc, right? You are already aware that this is not a BSc program, right? This is a B-Eng program, right? Bachelor of Engineering final year program. So that you should be aware of, right? So this is not BSc. In Sri Lanka, I think we have BSc in engineering, right? But this is the UK program. This is Bachelor of Engineering in Electrical and Electronic Engineering. And part of you should be from Bachelor of Engineering in Mechatronics, right? I know this consists of 2 batches, right? B-Engine Electrical and Electronic Engineering and B-Engine Mechatronics, right? If I'm not mistaken. Yeah. Hope that is clear to Sid, right? Okay. Uh, of course, you can talk even, right? You can type and you can talk even. It's okay. Any other background related questions? Okay. So anyway, I am not going to go through this chapter from the beginning again, right? Because Mr. Prathipan actually went through this thoroughly. He could not complete it, I know. So I'll be basically starting from where he stopped, right? So before going there, if you have any specific doubts, if you couldn't understand any specific concepts in this chapter, I'm more than happy to clear them out now. Anyone? Uh, yeah, NVQ level, I think this is level 5, right? I have to look up on this, right? So NVQ is the local framework, right? So let me get back to you on this, right? Yeah. So I have to go through this. NVQ is the local, framework, right? But according to the British framework, so this is level 6, right? This is the bachelor's level, right? So this question of Nirupa Ellavala, I'll get back to you soon, right? Because I have to go through this NVQ, right? Uh, Anything else? Uh, Dulan, which document you are referring to? Yeah, I think Mr. Shanaka has shared us the NVQ documentation. Yeah, this is also called SLQF. Yeah, so SLQF level 6 is the bachelor's honors, right? Yeah, so it should be level 6. So this is where you are. This is the qualification that you are going to pursue, right? And this is NVQ. So you can see here, yeah, so NVQ is defined up to level 7, which is bachelor's. It is not the honors program, right? So then NVQ is basically vocational. It's a vocational qualification, right? So it's defined up to SLQF level 5 or bachelor's, right? So what you are going to pursue now is SLQF 6 bachelor's honors, right? So that is the degree program that you are following now. SLQF level 6 bachelor's honors, and that is not defined under NVQ because NVQ is basically a vocational qualification, right? I hope that's clear to you. Yeah. I hope Ellava's question is now clarified. Nirup Ellavala. Okay. So NVQ is not defined for this particular qualification, right? Because it's a vocational. NVQ is for vocational kind of qualifications. Yeah, thank you, Mr. Shanaka. Right. I think everything's clear now. Back to Dulan. So you are referring to my PowerPoint, right? So Dulan's referring to the PowerPoint that I opened, right? Power computations. So that is available on the Google Drive, right? So if you open your Google Drive folder, right? So for triple E, right? So it's in here and FPC, right? So we are referring to this, right? And for mechatronics, right? I think that's here. So this is maintained by Mr. Abitha. Is that clear? Yeah, I think so. Right. Okay, so my plan was to start from where Mr. Pradeepan finished off last time, right? So if anyone wants me to go back and explain any concepts under these power computations, right? I can of course go back and help you. Okay, I'm assuming no such requests. So then let me start from where Mr. Pratipan finished off. One thing I wanted to emphasize that, so we are heavily depending on inductors and capacitors in power converters, right? So then you should have a thorough understanding of how these reactive elements, inductors and capacitors are reactive elements, right? Reactive elements. So that means they are basically energy storage elements, right? So they can store energy and they can release that energy when wanted, right? So then they basically do not consume energy, right? So they are basically energy storage elements, right? So if I am to explain to you the operation of an inductor, right? Say we have an inductor, right? Mind my drawings, right? So we are energizing an inductor using a certain source, right? So this is a source, some source. So this is an inductor. Now according to passive convention, right? So this will be the current is entering. So when we consider this inductor as a load, right? So the current is entering the positive terminal of the inductor, right? So this will be VL, the voltage across the inductor, right? Now, when the inductor is energized by a source like this, what happens is this inductor basically stores energy, right? How does it store energy? Can anyone tell me? In the form of what? In an inductor, in a form of what the energy is stored? Can anyone tell me? In an inductor, in what form the energy is stored? Can anyone tell me?
Hello?
Yeah,
So form of magnetic field?
exactly. Right, exactly. So then in an inductor, so in a magnetic field, the energy is stored. That means, so when you energize the inductor, there will be a magnetic field build up, right, around the inductor, right? So we are not going back to those, magnetic theory, right? So then you know that when you energize an inductor, so there builds up and magnetic field, right? So then, so there will be, of course, a current, right? Current through the inductor, right? Until the energy is fully stored, right? The one thing that is very important for you to understand in this case is, right, the current through an inductor, the inductor does not like the current through it to change. That is a very important observation here, right? Inductor does not like the current through it to change suddenly, right? That you should know. For example, if we suddenly disconnect this circuit, right? So there's a switch here. So you suddenly you disconnect it. So now what happens is now there's no current path to flow, right? So then inductor does not like this to happen, right? So what it will does is basically it will try to maintain the same current. So the only way to maintain this current is basically, so it will allow this magnetic field to collapse, right? So this magnetic field will collapse, right? So in such a way that right? So let me use another color here, right? The polarity, the voltage polarity across the inductor will switch to this, and now it will be like a source, not a load. So then, when it's according to the power conservation, right? So the current will leave this end, right? So that means, so the same current will then be maintained, right? Because of the collapsing of the magnetic field, what will happen is the voltage polarity across the inductor will change, and that will basically maintain the same current flow through the, it will try to maintain the current flow through the inductor. So if there are some other element across this inductor connected, so the current will of course flow through that, right? So that you should understand. So this is what happens in an inductor. So this concept is extensively used when we analyze power converters, right? So the inductor does not like its current to change suddenly. So then it will try to maintain the same current through it, right? So then we use this nature of an inductor to maintain constant current in a power converter, right? We use an inductor to maintain a constant current uh, in a power converter. So we'll in detail discuss this later on, right? A capacitor, right? A capacitor is actually a dual, right? A dual of an inductor, no? It's a dual of an inductor, right? Can anyone tell me, say we have a capacitor like this connected across some source, right? And say we have some load here as well, some load connected across it, right? So when this capacitor is energized, there'll be a voltage drop across. The capacitor will store energy so that there'll be a potential drop across it, VC, right? So then the current will flow in this way, right? Okay, then, so I said a capacitor is basically a dual of the inductor. So that means the inductor does not like its current to change rapidly, right? So then if the capacitor is the dual of that, can anyone tell me what is the nature of a capacitor? Can anyone tell me?
Hello, sir.
Yeah.
Electric field.
Uh, so yeah, that is an answer to a question. If I ask, okay, in what form the energy is stored in a capacitor? So that should be the answer, right? So
Electric
that is,
charges.
yeah, in an electric field, the energy will be stored, right? So my question is, now in an inductor, the inductor does not like the current through it to change suddenly. Likewise, can you tell me a feature of a capacitor in terms of something like that? Of course, yes. According to Dilantha, yes, voltage. So when a capacitor gets charged, right? So there will be a certain voltage across it. So the capacitor does not like that voltage to vary suddenly, right? For example, now say you disconnect this circuit right after the capacitor getting fully charged, right? So then what will happen is the voltage across the load, say VL, will try to go down, right? So but what the capacitor is now going to do is it will simply reverse the current direction, right? So then it will become like a source, right? So then it will simply reverse the current. It will not reverse the polarity of the voltage, but it will simply reverse the direction of the current, and it will simply supply the current through the load, and it will maintain the same voltage VC across the load, right? So that is the duality between these two components, the inductor and the capacitor, right? So capacitor will simply try to maintain the same voltage across it, so then it has the smoothing effect, right? So it can simply maintain a constant voltage across something, right? Likewise, in an inductor, right, inductor can basically maintain a constant current through it, right? So you should understand this duality, right, between these two reactive components, and these two elements are very important, without which we can't actually design any of these power converters, right? They are very important electronic components, right? So that I wanted to emphasize, right? uh, okay, hope that's clear. Any doubts there? Okay, so let us move on then. And this concept is also very important, the effective value, the RMS values of voltages and currents, right? So RMS value is simply what? So this is a means to measure the strength of an AC signal, right? It's an average, right? Root mean squared, right? So like a DC voltage, so if we can deliver a certain power, right? So say we have a DC source, right? Say we have a DC source, right? Having VDC, right? So using which we can deliver some power P to a load R, right? But so then the strength of this source is simply VDC, right? But what about AC signals? How do we measure the strength of an AC signal? To measure the strength of an AC signal, we use the RMS value. So what you do is simply, so the effective value or the RMS voltage or current is simply defined as the voltage or current, right, that is as effective as the DC voltage in supplying the average power. So then using this effective, V effective or I effective, we can deliver the same power P to a load R, right? So then you know basically how to find that VRMS or IRMS. So you have to simply get this root mean square value of the voltage or the current, right? So then that will simply give you the strength, right, of an AC signal, right? It's like a DC value of an AC signal, right, or the effective value of an AC signal, right? So this should be very clear and very important for you to understand the effective value or the RMS value of an AC signal, right? Okay. Okay, so then I think this is where you stop your discussion, right? And of course, I would very much like this to be like a discussion, right? So instead of me keep talking, so I would like you to, participate, right? At least by asking questions or adding something, right? Yes. So let us do this as a discussion, right? So then, so far, right, we have discussed the average power, right? So which is simply what? So you compute the average value of the power within one period, right? So then you simply integrate PT, which is of course VTIT, right, throughout a period, right? And you simply divide that integral by T, right? So then you get the average power, right? I think you did some examples there as well, right? So then another type of power, right, that you should be familiar with, which is the apparent power, right? So what is apparent power? So the apparent power is simply the product of RMS voltage and RMS current magnitudes, right? So we use the symbol capital S to denote apparent power, right? And we measure apparent power in the units VA, volt ampere, right? And this is mostly used in ratings of power equipment, like in transformers. You may have seen in VA units, right? So certain ratings are given in certain power equipment line transformers, right? So then how you calculate apparent power simply is you simply get the product of the RMS voltage and the RMS current magnitudes, right? And you know how to calculate the RMS values, right? Uh, okay. Then the power factor, which is also very important. Is there anyone who wants to talk? Any doubts? I can hear something.
Hello.
Yeah.
So is it some more questions for you? Is it
Yeah.
VRMS, how will be calculated? VDC over square root.
Sorry, I couldn't hear some part of your speech.
Yeah, VRMS, the
Yeah.
RMS voltage is equal to VDC over square root, is it? The equation?
No, no, no. VRMS is a integral, right? So then what? How you calculate VRMS is you integrate, right? Your yeah. So what you do is you integrate the square of your voltage or current signal over one period, right? Then get the average. So that means you divide it by T, then get the square root. So RMS means root mean square, right? So then what you do is, so if you are computing the RMS value of a voltage, right? So then you have this instantaneous signal VT, right? So then you square it, right? And you integrate it over one period. That means from 0 to T, right? Then you divide that value by T, then you get the square root of it, right? And if it is IRMS, right? So you consider the current signal, the instantaneous current signal, get the square of it, integrate it through a period, then divide that value by T, then get the square root. Is that clear? That's how you compute the RMS value.
All right. Okay, sir, sure.
Right. And this relationship is there, right? If you want to find the RMS value, if you know the peak value of a sinusoid, this applies to sinusoids, right? So if you have a sinusoid signal, which is a periodic signal, of course, and if you know the magnitude of it, the maximum value, right? The peak value, which is Vm, then you can, of course, find the VRMS. So you simply divide that peak value by √2. That is also there. But for a general signal, right, right? A periodic signal. How you calculate it? Simply square it, integrate it over one period, divide it by t, then get the square root, right? Hope that's clear. Right. So yeah.
We should to know the equation how will be verified or they will given the exam time.
Normally at this level, right, level 6, you don't, derive expressions, right? Most of the expressions, so when you use them, you will of course memorize them, right? Or if the equations are too lengthy, so there will be an equation sheet.
Sure.
Right? Okay. Right. So apparent power, we have already discussed. So any other doubts? Okay. Right. Then the power factor, right? So power factor, right, of a load is defined to apparent power. So now you know how to find the average power and you know how to find the apparent power, right? So then the power factor is simply the ratio of the average power to the apparent power, right? So average power is capital P, right? And the apparent power is capital S, and you already know how to calculate it. That is simply the product of PRMS and IRMS, right? Especially in sinusoidal AC circuits, right? Power factor can be considered as cos theta. Remember, this applies only to sinusoidal AC circuits, right? In a sinusoidal AC circuit, the power factor is simply cos theta. So what is theta here? So theta is simply the phase angle between the voltage and the current of sinusoids, right? It's the difference, right? The phase angle between the voltage and the current sinusoid, right? So this applies when both the voltage and currents are sinusoids, right? But in most of the cases in our discussion in power conversion, right? So we are dealing with non-sinusoidal signals, right? So we are dealing with signals like, sawtooth signals, right? Square wave signals. So in such a situation, right, we cannot use this definition. So we can't use power factor is equal to cos theta, right? So in such a situation, right, we will have to use the this expression, right, which is the more general form of it, right? So we'll have to use this expression because we are not dealing with sinusoidal signals in most of the cases in our future discussion, right? But if you are dealing with voltages and currents which are sinusoids, of course, then you can consider the power factor to be cos theta, right? So theta is simply the phase angle between the voltage and the current, right? Hope that's clear. Okay, then power computation for sinusoidal AC circuits, right? So then in general, right, voltages and or currents in power electronic circuits are not sinusoidal. So that I mentioned already. In power electronic circuits, so we are dealing with switches, right? We are dealing with inductors, capacitors, right? So those current and voltage waveforms in most of the cases are not going to be sinusoidal, right? It could be like, sawtooth in most of the case, right? So then in certain concepts we have defined so far we cannot use, right? So then when we deal with non-sinusoidal signals, but of course those signals are periodic, we can identify a period, right? Non-sinusoidal periodic waveforms, so we are going to deal with such waveforms, right? But we cannot use the concepts we have defined so far. The reason is those concepts, those expressions are defined for sinusoidal signals. So then how do we deal with these non-sinusoidal periodic signals. Can anyone suggest any methods? Right? So we are going to deal with non-sinusoidal voltages or currents, right? So then we cannot use the concepts or expressions we have defined so far that are of course applicable for sinusoidal signals, right? Then can anyone make any suggestions how can we use those concepts or expressions defined for sinusoidal signals, right? But of course we don't have such signals in our analysis. Anyone? I assume that you may have heard of this particular concept, how to deal with non-sinusoidal signals, but still to analyze them using the standard, concepts. Anyone? Okay, right. So then how we are going to deal with such non-sinusoidal periodic waveforms are to use the Fourier series of sinusoids, right? So we can, of course, I'm sure you are familiar with the Fourier series of sinusoids, right? So we can decompose, right, any periodic non-sinusoidal signal into an infinite sum of sinusoidal periodic waveforms using the Fourier series, right? So that's the definition of Fourier series, the use of it, right? So Fourier series is simply a tool using which we can decompose a non-sinusoidal periodic waveform into an infinite sum of sinusoidal periodic waveforms, right? I'm sure you are aware of that, right? So we are basically using the Fourier series. So then we decompose our non-sinusoidal waveform into a series of sinusoidal waveforms. Then we apply our standard concepts to each of those sinusoids and combine them, right? That is how we do it. Is that understood? So we use the Fourier series to decompose our non-sinusoidal waveforms into a series of sinusoidal waveforms. For those sinusoidal waveforms can now be treated with our known expressions, the defined expressions that we have defined so far, right? So that's how we deal with such non-sinusoidal periodic waveforms. Is that clear? Just have you understood that concept? It's a very simple concept where we use this tool, Fourier series, to decompose non-sinusoidal periodic waveforms so that we can apply those power computational concepts into those sinusoidal waveforms and combine them. So we can get the combined effect, right? Is that understood? Okay, right. Okay, then let's move on, right? For any element in an AC circuit, so say we have an instantaneous voltage Vt, which is defined to be Vm cos omega t plus theta, right? So theta is the phase angle of this voltage, right? Then It, instantaneous current waveform, right? So Vm is the peak voltage, Im is the peak current, right? So then It is Im cos omega t plus pi, right? So pi here means what? The phase angle of this current, right? Then you know how to calculate the instantaneous power. So this you have already in the beginning of this chapter done, right? So instantaneous power PT is Vt into It, right? So then you simply get the product of these two, right? So you get the product of Vt and It, right? Then using this trigonometric identity, right? So you can transform this into this. So then PT is simply, So you are applying cos A into cos B like, so take out Vm and Im, right? So then you have half, right, cos, right, half cos A plus B. So then A here is omega t plus theta, B here is omega t plus pi, right? So then A plus B means then omega t plus omega t, 2 omega t plus theta plus pi, right? So then that is cos A plus B. Then cos A minus B, so omega t cancels, right? Then theta minus pi, right? So then half becomes here. So then PT is simply Vm over 2 cos 2 omega t plus theta plus phi plus cos theta minus phi. So that is PT, right? Then what is the average power? So then you know the definition of the average power. So what you do is you simply integrate the PT signal over one period and divide by T, right? So when you do that, so then Vm Im over 2 is a constant, you take it out, right? So then you integrate your PT signal, which is this part of it, right? And of course, a part of this P is missing. What is that missing part? Can anyone tell me? So that is not a mistake here. So that pass had been, left out deliberately. Can anyone tell me, is there any missing part in here? Anyone? So you look at this expression, P is 1 over T, the integral 0 to T, Pt dt, and so Pt has been applied here. So when you apply that, is there anything that has been left out? Anyone? Anything that has been left out? Which is of course not a mistake. Anyone? Have you noticed that? Yeah, 1 over T is left out, right? Can you see here? So 1 over T, so there should be a, 1 over T. So actually there's no point putting this one here. You will see why, right? So that is the, when you do the integral, so you will see that. Okay, so if you have to do this, evaluate this integral, right? How do we do this? Can anyone tell me what this is going to equal? So what about this part of it? Anyone? What can you say about this part of this integral? Anyone? So this is integration, not power electronics. So this is a constant, right? There's no t terms here, right? So this is simply a constant, right? So then this will be like, so if you have to write Vm, right, Im over 2. So there's a t here, right? 1 over t integral 0 to t, right? So this pass cos, so this will be cos theta minus phi dt, right? So that will be there. Then what about this part? Anyone? Can anyone tell me when you integrate this part cos 2 omega t plus theta plus phi over dt. What will happen? So when you integrate, so this part is like a sinusoid, no? It's a periodic signal, right? So you are integrating a sinusoid over one period, right? Over one period. So integration means what? So you are getting the area under the curve, no? You are getting the area under the curve, but this curve happens to be a sinusoid, and you are considering this sinusoid over one period, right? So when you consider a sinusoid over one period, right, half of that signal will be above the curve, right, above the axis, no, x-axis, and half of will be below. Half of it will be positive, half of it will be negative, right? So when you get the get the sum of it, when you sum the areas, right, there are two areas, one is positive, one is negative. So when you combine them, what will happen? So that will be 0, no? So that integral, that part will be 0. That you have to understand, because this is a sinusoid, right? It's a cosine, of course, but it's a sinusoid. So over one period, when you get the integral, the result will be 0. So then the only significant term in this integral will be this part, right? So when you evaluate this integral, right, so then it will be something like this, because here cos theta minus phi is a constant, no? So you can even take that out, right? You can take that out. So then Vm, Im, cos theta minus phi, there will be a 1 over t, right? Here there will be dt, no? So when, so it will be like 0 to t dt, right? Right? So what you have here will be what? Vm over 2, right? Vm over 2t, right? So then if you simplify this, what will happen? So dt becomes t, right? So dt integral will be t. So then, so you evaluate over this duration, so that will be t minus 0, no? So then that t and this t will be cancelled. In addition to that, there will be a cos theta minus phi, no? So then the answer will be Vm over 2 cos theta minus phi, right? Hope that is clear. So the power, the average power for this particular sinusoidal AC circuit will be Vm over 2 times cos theta minus phi. Is that clear? Any doubts? Okay. Then you can alternatively, right? You can express this as this. How? Because so this can be expressed as what? Vm over root
So,
2. Yeah.
so this in the equation,
Yeah.
the phi equal to power factor, is it? Hello.
Phi equal to perfect. No, phi is the phase angle of the current waveform.
Oh.
Theta is
Right.
the phase angle of the voltage waveform.
All right.
Okay.
Sure.
Power factor is simply P over VRMS over IRMS. So that is a general power factor expression. But for sinusoidal AC circuits, we can say it's cos theta. Cos theta, theta here means theta minus phi.
Sure.
Okay.
Yes, sir.
Right. So then we can alternatively express this as Vm over root 2 Im over root 2, right, times this, right? This is the same, no? Root 2 into root 2 will be 2, right? So then Vm over root 2 is Vrms, you know that already. Im over root 2 will be Irms. So then alternatively, in terms of RMS voltages and currents, you can derive an expression for average power expression like this as well. Okay, is that clear? Okay. Okay. So I'm sure you heard of steady state. So in a steady state, I think under capacitors and inductors, you talked about steady state, right? So in steady state, that means the voltage and current waveforms are periodic, right? Periodic. There are no, instantaneous, voltages and currents. Everything is periodic. So then the system has achieved steady state, means the inductor currents and capacitor voltages are like they are periodic, right? So during that time, no net power is absorbed by an inductor or capacitor, right? No net means total. There's no total power absorbed by an inductor or capacitor, right? So in terms of that, we can define another power term, right? That is called the reactive power, right? So reactive power is measured in VAR. So it's like voltage ampere reactive, right? Voltage ampere reactive, right? And that is commonly used in conjunction with voltages and currents for inductors and capacitors, right? So reactive power is commonly used in conjunction with voltages and currents for inductors and capacitors, right? Uh, so then in most of the case, right, of course in steady state operation, right, so reactive power is characterized by energy storage during one half of the cycle, right, and during the other half of the cycle the energy is stored back, right? So that is what happens in a power system, power converter, right, under steady state. So what's mostly happening is that energy is stored during one half cycle. So where does the energy store? In an inductor or capacitor, right? And during the other half of cycle, the energy is retrieved, right? So that's why we say there's no net power absorbed, because if you consider one cycle, half of the cycle, there will be energy storage, and the other half of the cycle, the energy is given back to the circuit. So then the net power, there's no net power absorbed by an inductor or capacitor, because it's like charging and discharging, right? So that happens when the power converter is in a steady state. That you have to remember, right? Then reactive power is defined to be Q, right? It's termed as Q, right? And that is simply Vrms Irms times sine theta minus phi, right? So then complex power, right? In bold capital S, we write the complex power. So complex power is simply the combination of real power, which is the average power, of course, capital P. So that will be the real part of this complex number, complex power, plus Q. Q is the imaginary part of this complex power. So what is Q? Q is simply the reactive power. How do you measure Q? Q is simply Vrms IRMS sine theta minus phi. So that is the definition, right? So in other terms, right, in phasor notation, you can say S, the complex power is simply Vrms IRMS. What is this? Anyone? What is this star notation? In complex numbers?
Conjugate, sir.
Yeah, that is a complex conjugate. So that simply defines this negative side, the conjugate of this, right? So then the complex power, the bold capital is simply P plus JQ, which is of course a complex number. So which has a real part. So real part is the average power, and the imaginary part here is the reactive power, right? And in complex number notation, you can write it as VRMS, right? In complex number, then IRMS conjugate, right? So conjugate here means this negative, the difference, right? So
So
then
what is the
for
value
AC
of
circuits,
quantification?
sorry,
What is the
IRMS
value of
conjugate is, yeah, that is VRMS IRMS sine theta minus phi.
right.
So value, when you apply this, you will see, I mean, we will be doing examples, you will clearly understand that part. Okay.
Right, sure.
Okay. So then, okay. So then one more power term, right? That is the apparent power. So this is not the boldest, right? So apparent power is the italic S, right? What is apparent power? That is the magnitude of that complex number. That is the complex power, right? So mod S here means the magnitude, right? The magnitude of this S, P plus JQ, right? So how do you get the magnitude of a complex number? So that is, in this case, P squared plus Q squared square root, right? So then that will be the apparent power, right? So it is important, right, in this complex power and power factor of cos theta minus phi, right, are special cases. Why? Because power factor is cos theta minus phi only for sinusoidal AC circuits only, right? But for non-sinusoidal circuits, you can't apply that. Is that understood? The power factor for non-sinusoidal voltage and currents, it is not cos theta minus phi. We already discussed that, right? The power factor for that will be P over Vrms over IRMS or P over S, right? You have to understand that for non-sinusoidal AC circuits, power factor is P over S, not cos theta, right? Cos theta is only for sinusoidal AC circuits only, right? In general, power factor is simply P over S, right? Okay. Okay, then back to our relevant discussion, right? Power electronic circuits, right, typically have voltages and or currents that are periodic but not sinusoidal. I mentioned this already, right? Because we are dealing with switches, electronic switches, inductors, and capacitors, right? So the voltage and current waveforms are not going to be sinusoidal, right? So then, but they are periodic in the steady state, they are periodic, right? So then we are going to deal with periodic non-sinusoidal waveforms in our future discussion, right? Then how do we do the power computations for such periodic waveforms? So as I mentioned, so we are using the Fourier series, right? So we are using the Fourier series to describe non-sinusoidal periodic waveforms in terms of what? In terms of a series of sinusoids, simple sinusoids, right? Then we can apply the power relationships to each of those components and combine them, right? Is that understood? So that is how we are going to deal with those periodic non-sinusoidal waveforms that we are going to deal with later on, right? Hope that is clear. Okay. Okay, then to the Fourier series. So now we are not going to, go into details of, the theories of Fourier series, but we are simply going to mention it, right? So a non-sinusoidal periodic waveform can be described by a Fourier series, right? So what we do is we use the Fourier series, right, to decompose a non-sinusoidal periodic waveform as a series of sinusoids, right? So the Fourier series is denoted by FT. Fourier series is the series A naught. This is the A naught is the DC component of this, right? And an infinite sum of some sinusoids. So there are two components, a cosine and a sine, and there are two coefficients, a and bn, right? So a naught can be computed using this expression, a n can be computed using this expression, and bn can be computed using this expression. Of course, you don't have to memorize this, right? Fourier series, this expression you don't have to memorize, right? But you should know this is a very useful tool. You should know how to use it, how to use to decompose a non-sinusoidal periodic waveform into a series of sinusoids, right? Okay, another way, right? So we can use this expression again, and this is an alternative expression for a Fourier series, right? Ft, the same Ft, that is A naught, the DC component. Now this has only a cosine term, right? So this is again an infinite sum of a cosine which has the coefficient Cn, right? So what is Cn? So Cn is computed using An and Bn again, right? So A and Bn, you know how to compute. In the previous slide, you have the expressions, right? And T time is computed using this tangent, right? And another expression for the same Fourier series is that A naught, the DC term, plus an infinite sum of sinusoids, right? So here also you have Cn, right? Same Cn and a different T time. Now here T time is different. Here it's tan inverse minus Bn over An, but here it's tan inverse An over Bn, right? So you can use either of term A naught is a constant, right? It's a DC term, right? Which is the average value of Ft, right? And that simply represents a DC voltage or a current, right? The coefficient C1, right, when n is 1, right, is the amplitude of the term at the fundamental frequency, right? So when we deal with power converters, which has, of course, switches, right? Switches simply, can be electronic switches like transistors, right? So when we switch on and off signals, right, that will give rise to, harmonics, something called harmonics. So harmonics are simply multiples of frequencies. When you switch a signal, right, using whatever a switch, that will give rise to harmonics. So what is a harmonic? harmonic is simply a multiple of frequency. For example, omega naught, right? Omega naught is the fundamental frequency. Say you have a signal operating at 50 hertz, right? So your input signal is operating at 50 hertz. So then your fundamental frequency is 50 hertz. So that is omega naught, right? But when you switch this signal using whatever switching technique, that will give rise to harmonics. Harmonics means multiples of frequencies. That means that will give rise to 2 omega naught. That will give rise to 3 omega naught. So that 2 omega naught is the first harmonic. 3 omega naught is the second harmonic, and so on. So likewise, there will be mostly an infinite uh, sum of generation of harmonics when you switch a signal. So that happens when you design your power converters. You will see later on. So then generation of harmonics is bad, right? So that will give rise to distortions. You will see. So in terms of THD, total harmonic distortion, we measure this, right? You will see what is total harmonic distortion later on, right? So simply when you switch a signal that is unavoidable, of course, we have to use switching converters because they are efficient than linear converters. So you'll learn that later, right? So unavoidably, there will be harmonic distortions. When you switch a signal, there will be harmonics generated, right? Omega naught, that is the fundamental frequency, and there will be signals operating at 2 omega naught, 3 omega naught, 4 omega naught, and so on, right? So then we'll have to employ certain filters to overcome these. So then we'll be discussing those in detail during this discussion of this module, right? So up to now, you should know that, right? So we are dealing with mostly non-sinusoidal signals in our power converters, right? So then definitely we'll have to use the Fourier series to decompose our non-sinusoidal signals. Then only we can apply our power concepts in order to evaluate the signals. All right? Is that clear? Any doubts? Anyone has any doubts? Don't worry, these concepts we will discuss in detail later on. So before going into switching conversion, we will first go to linear conversion, right? So then step by step, we will be designing or discussing switching converters. Of course, that is new, right? Okay, let us move on. Then what about RMS values of those Fourier terms, right? So in the same way, we can compute the RMS values of the Fourier series by simply taking the sum of the squares of the components and getting the square root, right? So capital F here means the Fourier series. So the Fourier series has a DC term, right? A naught, then the RMS terms of the coefficient C, right? So we have set of coefficients. If you go back and see, right? So we have this C and coefficient, right? So then to get the RMS of this, we divide that value by √2. Then you square it, right? Then get the infinite sum. Then you get the square root of it. So then you get the RMS value of the Fourier series, right? Is that understood? To get the RMS value of FT, the Fourier series, what we do is, right, we consider the RMS terms, right? Basically, there are infinite number of terms in that Fourier series. You square them and add them and get the square root of it, right? So that will be the RMS of that Fourier series. Don't worry. I mean, sometimes this may be confusing. Too much, content. Don't worry. But when we apply this in certain examples, applications, we will understand this very clearly, right? I can guarantee that, right? Too much content, that I agree, right? But when you apply these concepts, you will clearly understand that. Okay, right, right. Then now you know how to get this Fourier series of an unsinusoidal signal, right? Example, say you have a VT, which is non-sinusoidal. Then using the Fourier series, you can decompose it. So this is the Fourier series of that non-sinusoidal voltage. We are using the Fourier series. Why? Anyone? Why are we using this Fourier series to represent this VT signal? Anyone? Why are we using this Fourier series expression to represent this VT signal? Anyone? Sellakumar, can you answer that question?
Sorry, no idea, sir.
Yeah, so why do we use the Fourier series? The first question. Where do we use it? Did you understand that?
This is a
Why do we?
non-sinusoidal.
Exactly, Sadiq. Yes, you understood it well, Sadiq. Yeah. Thank you for the answer. Yes. So then VT is not a sinusoidal signal, but it is a periodic signal. Right. So this is the reality. Now, when we are going to deal with power converters, we are mostly dealing with periodic non-sinusoidal voltages and currents. So then definitely we will have to use the Fourier series to describe such signals. That's why we are using the Fourier series expression to describe this VT and IT. Sellakuma, is that clear?
Yeah, sure.
Okay. Any other student who couldn't understand that? Because this has to be understood very clearly. Why we are using that Fourier series expression to describe that VT and IT. Anyone who couldn't understand that part of it? So this is still not power conversion. This is simply signals and circuits, right? And I hope everybody understood that part where we use the Fourier series to describe periodic non-sinusoidal signals, right? Of course, that we are going to deal with later on in our power converters, right? So then in this case, VT is described by this particular Fourier series. So it has a DC component V naught plus an infinite sum of Vn terms, right? Likewise, the current term is described using this Fourier series. So it has a DC term I naught and an infinite sum of In, right? Okay, then how to find the average power? If you know VT and IT, so we are using this general expression, right? So then that power will be the sum of components. So then we have to consider, so here you have components, right? There's a DC component and there's an infinite sum of V terms, right? And here there's a DC I term and the infinite sum of items, right? So then to get the total power, so what you do is you have to sum up each of those power terms, right? So then you consider first the DC term, that is V naught into I naught, right? Then we are using this term, we previously defined this, if you can remember, right? For those sinusoidal terms in the Fourier series, we are getting the infinite sum of VNRMS, INRMS. So that means there will be an infinite number of products of VRMS, IRMS, cos theta n minus phi n. Right? So in other words, so this P will be, right, V naught I naught plus an infinite sum of now, so you can simply RMS. So instead of RMS, you can write Vn max divided by root 2, right? Vn max divided by root 2 and In max divided by root 2. So root 2 into root 2 becomes 2, right? In the denominator, and in the numerator you have Vn max into In max. Is that clear? How you get this from this? Clear, right? So Vn RMS can be written as Vn max divided by root 2, right? In RMS can be written as In max divided by root 2. So root 2 into root 2 becomes 2, right? That is the denominator, and numerator becomes Vn max into In max. Is that clear? So then power in this case is simply right, the sum of all these components, right? So that is going to be the average power in this case, right? Okay. Okay, so further into application side, now assume, right, we have a non-sinusoidal source, right? Non-sinusoidal source means now definitely we'll have to decompose that source into many sinusoidal terms, no? So if the source is non-sinusoidal, we can decompose using the Fourier series into an infinite sum of sinusoidal source, including a DC source. No? So here this means infinite. This load, right? The power absorbed by this load can be computed or determined using the superposition. That means you first decompose this non-sinusoidal source into a sum of many sinusoidal sources. Then you compute the power, right, from each of those sources separately, right? You compute the power from each of those sources separately, then using superposition, you combine them. That is called the superposition theorem, right? So then in that way, you can find the total effect, the total current you can compute. Is that understood? So you have a non-sinusoidal voltage source. So if you want to find the power absorbed by the load, so what you do is you first decompose your non-sinusoidal source into many simple sinusoids. Then you find current in the load due to each of those voltage. Then you can find the power due to each of the voltage source, and then using the superposition you can combine them, right? So that is how you find the power absorbed by a load Then the source is non-sinusoidal, right? And the load is linear. Is that clear? Uh, Sahan, do you want me to repeat it again or did you get it?
Okay, sir. Signal problems.
Okay, you got it right?
Okay, okay, sir. Got it.
Yeah, because I think most of the part of the country is now experiencing heavy rains, wind and rain. So I think there's a reception problem. Okay. Anyway, so if you can't hear anything or if you can't understand, please disturb me. I'm ready to help you, right? Okay, I think then we can go on to a good example, right? Okay, then let us work out this interesting example, right? So this is non-sinusoidal source. So we have a VT, which is a source, which is non-sinusoidal. How do you say that is non-sinusoidal? Because it's given, no? So it's given a non-sinusoidal periodic voltage has a Fourier series of Vt, that is 10 plus 20 cos something plus 30 cos something, right? So then Vt is of course non-sinusoidal, no? It's non-sinusoidal, but it has been now decomposed using the Fourier series. Now you can see it has sinusoidal components in it, including a DC term, right? But it is given that Vt is non-sinusoidal, right? And it has a linear load. So now in this case, load is a combination of a resistor and an inductor. Both are linear loads, so then it's a linear load. In combination, it's a linear load. The question is, determine the power absorbed by the load. Can you try this now? Very useful, interesting example, right? So VT Fourier series, you don't have to find it. It's given, right? Value of the resistor is 5 ohms. Inductor value is 15 millihenry. Now we want to find the power absorbed by the load, which is in combination the resistor and the inductor, right? Load in this case is the combination. This combination is the load. Is the question understood before going into the answer? Questions understood, right? Okay. So then let us move on, right? So then what we have to do in this case, right? Now we know the voltage component. We have decomposed it. Now what we want to find is IT, the current components due to each of those voltage components, right? So each of those voltage component will give rise to a certain IT, right? So then we'll have to find each of the IT terms, right? So here we have how many current terms, how many voltage terms? Anyone? How many voltage sources are here according to the Fourier series? Anyone? How many voltage components are here?
Three, sir.
3. Yes. So then how many current terms will be there?
One.
3. Again 3. There will be 3 current terms due to each of the voltage terms. So then we'll have to now first compute each of the current term and combine them and find IT. Is that clear? Okay, then we'll go ahead then find the current terms, right? So then first current term will be due to the DC voltage 10, right? How do you find it? What is current? V is equal to IR, right? So then I will be what? V over R, right? Yeah.
Yeah.
So when we consider R, do we consider both the resistor and the inductor? Anyone?
Only resistor.
Yeah, because why?
Because this is a non.
This is DC, no? The source is DC.
Yeah.
The source DC means inductor appears as what? Inductor appears as inductive reactance, XL. What is it? J omega L, no? Or 2 pi F L, no? So in this case, what about F? DC means?
Frequency.
Yeah. DC means what is F?
Frequency.
Yeah,
0.
frequency 0. So then what is XL? XL is like a resistance, no? Inductive reactance. So then this will be 0, no? So then inductor looks like a short circuit, no? In a DC circuit. Is that clear? Inductor looks like a short circuit, no? Because the reactance is 0. So then when you consider the DC voltage term, right? To compute IT, you will have to consider only the voltage and the resistance only, no? Is that clear? So I naught will be 2 amperes. Is that clear? Anyone? So due to V naught, which is the DC term of the voltage, the current will be 2 amperes. Is that clear? Anyone? Anyone who couldn't understand that part? Sellakumar, is that clear?
Yeah, sure.
Okay, then we'll go on, right? So then we'll consider the next component. 20 cos 2 pi 60t minus 25 degrees, right? So then what is the I component due to this? Anyone? So what is IT due to that voltage component? Anyone? This will be this over this numerator. Can Sellakumar tell me?
20.
Sorry?
20.
20, yes.
And,
Yeah.
yeah, angle is minus 25 cos theta.
Yeah, we use the polar notation.
Yeah.
Is that clear? 20 is the magnitude, so 25 is the angle, phase angle in polar notation. Divided by what? Divided by the load, no? In this
Yeah.
case, we can't disregard the inductance because it's frequency dependent. Now it has 60, the frequency, right? So the frequency is not 0, so then there will be an effect, no? So then this will be R plus what? J
Pi
J
plus J
omega,
omega L. J
yeah,
omega
pi
L.
plus J
Omega L.
2 pi 60
F.
L, no? So L in this case is milli, so then that will be 0.015, no? Is that clear? So this is the impedance, right? Any doubts? Okay.
Sir,
Yeah.
can you explain again, sir?
Yeah. So then now what we are going to do is we are going to compute each of the IT terms due to each of the voltage terms. Is that clear?
Yes, sir.
Right. So then we first consider the DC term, that is 10 volts. Then we computed using IT is equal to what? V over the impedance, no? Let's say the impedance is something called X, right? So then this will be like V over X, no? So then the voltage in that case is 10. X, since this is a DC voltage, there's no effect on the inductance because X, the impedance is what? R plus, because this is a series connection, J 2 pi F L, right? This part is 0 for this particular DC voltage, right? So then you will have only 10 over 5. Is that clear, Sadiq?
Yes, sir.
Okay, then for the next component, that is 20 cos 2 pi 60 t minus 25 degrees, we are using the same V over X. Now here voltage is a phasor, no? It's a complex number. It's a phasor. There's a magnitude and a phase angle. So then we use the polar notation to denote that V. So that is 20, the angle minus 25 degrees. Is that clear?
Okay, sir. Okay, sir.
Right, then X is R plus J2 pi FL. So J2 pi F is 60, the frequency. L is the inductance in Henry. So this is millihenry, so you convert it into Henry, so it becomes 0.015. Is that clear, Sadiq, now?
Yes, sir. Thank you, sir.
Okay. So then let us simplify this. So let's say that is I1, right? So now at the same time, you should know how to use the calculator to do this computation, right? So you will use a scientific calculator, right? But in my case, I have a scientific calculator, so but I can't show it to you. So then I will use the software form of it. I have this one. So let me use my calculator here to do the to find I1, right? So make sure when you use this calculator, the mode of operation is complex. Mode 2, then your angle are going to be measured in degrees, so then it should be in degrees. So I hope you all have a scientific calculator, right? And you know how to use it, right? So let us do this computation. So we have the denominator 20, the angle minus 25 degrees divided by 5 plus 2 pi into 60 into 0.015 JOI in this case, right? The answer is, so we get the answer in rectangular form, so then we'll have to convert it into the polar form. So let me do the conversion. So that will be this form, number 3. Right. So the answer will be 2.65, right, approximately. And the angle is minus 73.5 degrees. That's correct, right? Okay, so then our I1 phasor, so I1 in bold means it's a phasor, a complex number. So then that is a magnitude of 2.65 and an angle of minus 73.5. Is that clear? Likewise, can you compute the I2 term? Can you try that now? I2. You can do it yourself now. I2. Can you try that now? And tell me the answer. I'm waiting for you to give me the answer. Anyone? The answer? What is the magnitude of I2? So you will simply have to divide 30 and the angle 20 by the same impedance, right? 30, 20 divided by the same impedance. 5 plus J2 pi 60, 0.015. Right, so 30, 20 divided by 5 plus, sorry, in this case, different frequency, no, different frequency, different angle, right? 30, 20, so then the inductor will be affected differently, right? So that is 5 plus J 4 pi 60 into 0.015, and the magnitude is 2.43, the phase angle minus 46.2. Is the answer correct? Can anyone tell me, is that answer correct? Yes?
Yes, sir.
Correct, right?
Yeah, correct, sir.
Okay, I2. Okay, so then now you have computed the corresponding current terms, I0, I1 and I2. Now you can combine those current terms and find the the actual IT, right? So you combine I naught, there is 2, right? So then there is 2 plus 2.65 cos the same frequency minus that phase angle minus 73.5 plus 2.43 cos the same frequency minus 46.2. Is that clear how we approach this problem? The problem is not completed, but this is the first step. So you compute the load current first before computing the power. Is that clear? Any doubts? So you have simply converted your polar form into simply the sinusoidal form, phasor form basically, right? Phasor form, polar to phasor, right? Okay. So then what you want to do is determine the power absorbed by the load. So then how do we calculate the power? Using this, no, 2.259. P is V naught I naught plus, right, the sum of uh, each of the power terms, no? We are using 2059, that expression, right? So we will use that now. So first we will compute the DC term P naught. So we are using this expression 2059, right? First the DC term V naught I naught, right? So V naught is given, right? I naught you computed, right? So then P naught is 20 watt. Then P1 at this omega, right? Can you remember? At this omega, right? 2560, right? So P1 is using this part of it, Vn max, right? Vn max is there in the expression 20, right? In max, we have computed it, magnitude, right? Over 2 cos theta n, the phase angle of the voltage minus the phase angle of the current, right? The phase angle of the voltage is minus 25 minus the phase angle of the current, right? That is minus 73. So then minus minus becomes plus, no? Minus 73.5 becomes plus 73.5, right? So then you get the answer. Due to that VI component, the power absorbed by the load is 17.4, right? Likewise, the third voltage component, this one, at this frequency 4560, right? P2 is 30, that is the Vn max, Vn max 30, then In max divided by 2 cos the phase angle of the voltage minus the phase angle of the current, right? Phase angle of the voltage is 20, right? Minus 46.2, so that becomes plus, 20 plus 46, right? So that becomes 14.8. Right? Then you combine each of the power components, because that's what you have to do here, no? Combine them. So that becomes the sum of all these, so that will be 52.2 watts. Right? Alternatively, you can use this expression, P is equal to I squared RMS times R, right? Considering each of the terms, right? So here you have the DC value, so then this becomes simply 2 squared. Then the second current term, so that is peak current, so then 2.65 divided by root 2 makes it RMS, right? Then second current term 2.43, which is a peak current, divided by root 2 to make it RMS into the R value, right? So that becomes simply 52.2. Okay. In this case, we are not considering the inductor, because the average power absorbed by the inductor is 0, right? The average power absorbed by the inductor is 0. In this case, we are not considering the inductor's effect. If you use this method, you simply consider the resistor only, right? Is that clear? Any doubts? Make sure you work this out again, right? Work out this sum again, right, without looking at the answers, right, and see whether you can do it correctly. That's a very good example and useful too, right? Then now previously we had a non-sinusoidal source and a linear load. Now we consider a sinusoidal source, right, and a non-linear load, right? What is a non-linear load? Can anyone tell me what a non-linear load is? Any examples? Anyone? What are nonlinear devices? What is the first device that comes into your mind? Imagine the IV characteristic curve of a certain device, which is of course not a linear curve. Anyone? What is that device? Anyone? Yeah, motor. Motor is a nonlinear device. So what I was referring to was actually a rectifier. If you can remember the IV curve of a rectifier, which is not a linear curve, no? So then a rectifier is a good example of a nonlinear load, right? Then variable speed drives, you know, VSDs, variable speed drives. Then systems that use SMPS. What are SMPS? Switching mode power system. So the discussion that comes soon, right? The power converters that we are going to design soon will come under this category, switching mode power converter. So those are, of course, nonlinear loads, right? Okay, good. So when it comes to nonlinear loads and sinusoidal sources, right? So definitely the current waveform will not be sinusoidal. So it will simply give rise to harmonics, right? Assume your Vt, which is the sinusoidal voltage, is V1 sine omega naught t. So omega naught is the fundamental frequency t plus theta 1, right? And the current is not going to be sinusoidal, so then that is represented by this Fourier series as a DC term and an infinite sum of sinusoids, right? Then the average power absorbed by the load or supplied by the source is computed again using the same 2059 expression, right? Same expression like before, right? So this voltage does not have a DC term, so then this will be 0, no DC term. So it will have only a component that is corresponding to the fundamental frequency, that is V1. The rest of the V terms will be 0. There are no other V terms. There's only a V term corresponding to the fundamental frequency omega naught only. So then rest of the uh, power terms will be 0. So then only this will be non-zero, right? So then that will be simply this, right? So then instead of V1 I1 over 2, you can write V1 divided by root 2, I1 divided by root 2, that becomes V1 RMS, I1 RMS times cos theta minus phi t1. Is that clear? Right? So when you are dealing with sinusoidal sources and nonlinear loads, how you compute power, you'll be using this expression, right? V1 I1 over 2 cos theta 1 minus phi 1 or V1 RMS I1 RMS times cos theta 1 minus phi 1, right? Is that clear? Any doubts? Right? Too much content, I know, right? But we should be very clear when we apply them in examples, right? So don't worry, right? So this is the, as I told you, the tool set that you are going to use to analyze your power converters that you are going to design later on. So this discussion is very important, right? And that very important that you understand it clearly, right? So go through this again and again, right? Within the next week, before the next discussion, and make sure you understand this very clearly and get back to me if you have any doubts, of course, right? You should understand this very clearly. Okay. Note that the only non-zero power term is at the frequency of the applied voltage. So that is clear, no? Here, the only non-zero power term is at the frequency of the applied source, V1 RMS, I1 RMS, V1 I1, theta 1, phi 1, right? Only at the applied frequency, right? Applied voltage. The power factor of the load is computed using the same power factor expression, that is P over S or P over VRMS, right? So what is P here? Now we are replacing that P term being, previously computed. So then P is V1 RMS, I1 RMS cos theta 1 minus phi 1, right? The expression we derived previously. So then in this case, we have only V1 term, V1. So V1 RMS, IRMS, right? So then V1 RMS cancels, right? So then this becomes I1 RMS over IRMS cos theta 1 minus pi 1. So this PF expression is applicable to non-sinusoidal sources and nonlinear loads in systems where there's a sinusoidal source and a nonlinear load. So how you find the power factor of such a load in such a system is using this expression, that is I1 RMS divided by IRMS cos theta 1 minus phi 1, right? And RMS current is computed using the same expression. So this was represented before, right? So you simply square the RMS terms, add them, and get the root of it. So that will be the, so this is simply the Fourier series, right? Fourier RMS coefficients, right? So you simply square each of the RMS terms. For DC, it's simply the DC terms. For other terms, coefficient divided by root 2, square them, add them, and get the square root of it, right? So using this, you can simply find the IRMS value, right? Uh, so as I told you, for sinusoidal voltages and sinusoidal currents, you can simply use this expression to find the power factor. But this is not applicable for non-sinusoidal voltages, right? So this is also called displacement power factor, right? PF is also called displacement power factor applicable to sinusoidal voltages and sinusoidal current, right? Now, when we look at non-sinusoidal or nonlinear loads, right? So we have this expression, right? This expression. So in this expression, this part of the expression is called the distortion factor, or DF, right? DF is simply I1 RMS divided by IRMS, applicable to sinusoidal source and nonlinear loads, right? Then this distortion factor simply represents what? The reduction of the power factor, right? The reduction of the power factor due to the non-sinusoidal property of the current, right? Why? Because this is the, so this is PF in the previous case. So then PF in this case, right? So D, what D does to this PF is, right? It simply shows the reduction of the power factor due to what? The non-sinusoidal nature of the current here, right? So then you should understand that DF simply represents, right, the reduction of power factor due to the non-sinusoidal property of the current, right? So using this DF factor, then we represent the power factor, right, for this particular system where there's a sinusoidal source and a non-linear load, right, is simply DF times cos theta 1 minus phi 1, right? So that is how you compute the power factor of in a system where there's a sinusoidal source and a non-linear load, right? Very important concept. I mentioned this before also. Total harmonic distortion. So what is total harmonic distortion? Right? So this is simply a measurement of the harmonic distortion present in a signal. Right? So when you switch a signal, what happens is it introduces harmonics, right? Multiples of fundamental frequency is introduced due to the switching effect, right? So that will introduce distortion in the system, right? Then how do we measure that distortion? So that is using the total harmonic distortion, right? So this is a term. So this one simply quantify the non-sinusoidal property of a waveform, because a sinusoidal waveform has now been modified by many harmonics, right? What harmonics do to a system is it will distort the system, right? So without using certain filters, you can't remove that effect, right? So then that will simply distort a system, and you can measure, right, or quantify, right, that property, that distortion property using THD, right? We call it total harmonic distortion. So we normally represent THD as a percentage, right? You will know that the higher the percentage, the lower the percentage, the better, right? The better in the sense, it depends on what the system you are talking about, right? For example, say you are dealing with an audio system. Say you have an amplifier, right? So you are dealing with an audio system. Then how does THD describe the nature of that audio system? Can anyone tell me? In an audio system, if the THD is lower, what do you mean by that? Can anyone tell me? In an audio system, if THD is lower, what do you mean by that? Anyone?
Because of it has no switching components.
Uh, we can't say there are no switching components, right? We can say the distortion is less, right? In other words, right, you can say the component, for example, say loudspeaker, right, amplifier or microphone. In an audio system, those systems are there, no? There's a loudspeaker, there can be many loudspeakers, an amplifier or microphone or other equipment, right? So low THD means, right, those equipment produce more accurate reproduction of an audio recording. Is that clear? So low THD in such a system means, right, those equipment produce more accurate reproduction of an audio recording. That is what you can say if it is an audio system. Low THD means that. Is that clear? So then low THD is better in any system, right? But particularly if it is an audio system, then low THD means the system basically reproduces uh, an audio recording better. Is that clear? Clear, right? Low THD means the reproduction of a recording is done better, right? Then what about in a power system? If in a power system, if there's a low THD, what does it imply? So that implies lower peak currents, less heating, lower electromagnetic emissions, and less core loss in motors, right? If it is a power system, low THD means, again, lower peak currents, that is better, less heating. Heating means always waste, no? Less heating. Then lower EM emission, electromagnetic emission is not good. It will affect surrounding other equipment, right? Then less core loss in motors. So then the loss in motors are less. That is also good, no? right? So then lower THD in power system is also better, right, in terms of those aspects, right? Likewise, lower THD means always better, right? So those are some examples, right? So make sure you learn more, right? Okay, is that clear? Okay, then how is THD defined, right? So THD is the ratio of the RMS value of all the non-fundamental frequency terms. RMS values of all the non-fundamental frequency terms, right? So non-fundamental means n is not equal to 1. If n is equal to 1, that means there is a fundamental frequency. Now here we are looking at currents, RMS currents, the square of it and the sum of it. But we are summing only the squares of non-fundamental frequency related current terms, right? To the terms, to the RMS value of the fundamental frequency term. So here I1 squared RMS. So that is the definition of THD. Is that clear? So then square root of this part will be I1 RMS. So again, if I am to tell you, THD is simply the ratio of the RMS values of all the non-fundamental frequency terms. It's a sum divided by the RMS value of the fundamental frequency terms. In other words, so you can express IRMS, all the current terms squared RMS, then you subtract the fundamental term. Again, the same thing, no? You subtract the fundamental term from all the terms. It's the same thing, no? Divided by the same value. Likewise, so you can use one of these terms, expressions, to find the THD value. So we'll work out an example soon, then you will understand how this is done. And in another way to express the distortion factor, so you can relate using these expressions, you can relate DF into THD. So if you know THD, you can find the DF. If you know DF, you can find THD. So I'm not going to derive this, you can derive it using this. Using this, you can derive it, right? Okay. Any doubts? Okay, let us move on. Then reactive power, we already discussed this, right? And we compute it using this expression, right? And it is denoted using Q, right? So the reactive power is due to what? The inductors and capacitors in steady state. If you can remember the nature of power storage and retrieval, nature of inductors and capacitors, reactive power is there, right? How you compute is reactive power Q is VRMS IRMS into sine theta minus pi, right? Then again, the only non-zero term in reactive power is at the voltage frequency. Now, again, we are looking at sinusoidal source and nonlinear loads. So there we have only one voltage term, sinusoidal. So then Q can be computed using this, right? Because VRMS can be written as V1 over root 2, I1 over root 2, that becomes V1 I1 over 2, right? So with P and Q defined for the non-sinusoidal case, apparent power S must include a term to account for the current and frequency which are different from the voltage. So that means if the source is non-sinusoidal, right? If the source is non-sinusoidal, there will be multiples of voltages, no? So then the apparent power, right? So what is apparent power? If you can remember, this is P squared plus Q squared square root, no? So this is when there's a sinusoidal source. But when the voltage source is non-sinusoidal, right? So then this expression should have another term, right? Another term to account for the current at frequencies which are different from the voltage's frequency. So then we should have another term, in this case d squared, right? We call it distortion volt amps, right? So we use this expression traditionally, right, to calculate the value of the apparent power, right? So D is computed using V1 RMS into the square root of the sum of the squares of non-fundamental currents, right? So V1 RMS can again be written as V1 over 2, right? So then that will be the sum of the square root of all the current terms which are not the non-fundamental frequency related, right? So this is also important, right, to calculate the apparent power S, right, when we deal with non-sinusoidal voltages and currents, right? Don't worry. So we'll be using these in an example soon, right? So then you will understand how to use them. In addition to that, there are two other terms, right, used for non-sinusoidal currents or voltages, which are the form factor and the crest factor. These are just definitions, right? What is form factor? IRMS divided by I average, right? Crest factor, I peak divided by IRMS, right? Don't worry, you don't have to memorize this, but make sure that you should know that there are these terms that describes the nature of non-sinusoidal currents or voltages, right?
Sir, hello.
Yeah, yeah.
So where is coming from the D square D?
D is coming
Yeah.
from the fact that we are going to deal with non-sinusoidal voltages and currents, because up to this point we have considered sinusoidal voltages and currents. In this case we have only P and Q only. The apparent power is only related by P and Q. But when it comes to non-sinusoidal nature of power converters that we are going to discuss soon, right, will have effect from the frequencies operating at currents other than the fundamental frequencies, right? So this is due to the currents operating at frequencies which are different to the fundamental frequencies. Definitely this type of applications we'll be looking at, we'll be dealing with soon. Power converters, of course, will have to account for currents operating at frequencies which are different to the fundamental frequency. So D is coming from that fact. Can you see here? This fact here, of course, there's a V term operating at the fundamental frequency, but in terms of currents, there are many currents operating at non-fundamental frequencies. N is not equal to 1. Okay. So D is coming from that fact, because there will be multiple currents operating at different frequencies because of the non-linear nature of the loads that are in power converters that we are going to discuss. Because there will be switching mode power conversion involved in the systems that we are going to discuss. Don't worry, you might not fully understand that fact, but you will soon understand that. Otherwise, if we don't consider or incorporate this term D into this, we are neglecting the effect of the non-fundamental, the currents operating at non-fundamental frequencies. That is wrong. That is not correct. Is that clear, Selvakumar?
Yeah, that frequency will be changing time only. We will apply for the D, is it?
Exactly.
Or is it? All right. Okay, sure.
Exactly.
Thanks.
Because definitely we will be dealing with such circuits soon. Okay, in switching power converters, definitely those are the type of circuits we are going to deal with. Okay.
Thanks.
Okay.
Yeah, thank you.
Right. Example. Right. A sinusoidal voltage source of Vt, which is 100 cos omega t, omega is 377. V is applied to a nonlinear load. So this load can be like, switching mode component, right? Resulting in an unsinusoidal current, which is expressed in Fourier series. Now, can you see here, Sellakumara, right? Now, in this case, you can see IT contains sinusoidal contents operating at different frequencies. No, this is the kind of applications we are looking at. Now here omega is this. Now this is 2 omega, no, 3 omega. Okay, so definitely in this type of an application, D has to be incorporated. Okay.
Sure.
Okay. Again, back to the question, a sinusoidal voltage of Vt is applied to a nonlinear load, resulting in an unsinusoidal current, which is expressed as expressed in Fourier series, this, right? So it has 4 components, including a DC component. Determine the power absorbed by the load. Can you try this now? So how do you compute the power absorbed by this? This, no? The last expression, 262, V1 RMS, likewise. The 262, that is the expression that we are going to use, okay? Determine the power absorbed by the load. So then you'll have to compute. Now in this case, even though IT contains many components, will there be multiple power components? Anyone? According to this expression? No, right? There's only V1, I1, no? Because the source is sinusoidal, contains only one component, right? So then, even though IT contains many terms, right? When you compute the power absorbed by the load, right? All these terms, this term, this is V naught, this is V1, V2, V3, all those terms are going to be 0, no? Is that clear? And ultimately, we are using this expression, no? This expression, we are considering only V1 RMS, I1 RMS, cos theta 1 minus phi 1, right? V1 RMS is 100 over root 2, I1 RMS, that is 15, right? So how do you call that this is I1? How do you call that this is I1? This is not, and this is not I1. Anyone? Why are we using 15 here, not 6 or 2? Why are we using 15 here? Why are we considering 15 to be I1? It's because the frequency, no? Sorry?
So frequency we have to check.
Exactly. Yeah, the fundamental frequency, no? So the voltage is operating at this frequency, which is the fundamental frequency, no? So then I1 should also operating at that frequency, right? So then 15 is I1, right? Thank you. Yes, good. Okay, so then cos 30. Why it's cos 30? Because the voltage, there's no phase angle, no? So then the difference is 30, right? Difference is 30, right? So then the answer is 650 watts, right? Is that clear? So that is the power absorbed by the load. Then the power factor of the load, right? So how do you compute the power factor of the load? Using this, no? Power factor is df times cos theta 1 minus phi 1. So df is I1 RMS over IRMS, right? Or in general terms, you can use this as well. P is VRMS, PF is POS, P over VRMS, IRMS, right? Likewise, you can use 263 as well, right? So depending on what's available, so we can use one of those, right? So then to calculate the power, so we can use power factor, right? So we can use the general expression, right? This is the general expression, right? To find this, we need the average power. We have already computed it in the previous part. Then VRMS. How do you find the VRMS? The voltage V is given, no? That is 100. So you divide by root 2, you get VRMS. So that is this, no? VRMS. Then we need IRMS. So what is IRMS? So IRMS can be computed using this expression. This is also previously presented, right? Considering all the current terms, including the DC term, we can find the IRMS. So then we have the current terms 8, the coefficient 15, 6 and 2, right? 8, 15, 6 and 2. So 8 is DC, so then simply that. So 15 divided by root 2 squared, 6 divided by root 2 squared, 2 divided by root 2 squared, and sum of that and square root of that. So that will give you the RMS value, right? So apply all those values here, right? So you get the power factor as 0.66, right? Alternatively, you can use the equation 263 as well, right? So in 263, power factor is defined to be I1 RMS cos theta 1 minus phi 1 divided by IRMS. So I1 RMS, so you consider the I1 term and the RMS of it, that is 15 divided by root 2 cos theta 1 voltage phase is 0 minus 30 divided by IRMS. You computed that is 14 and you get the same answer here, right? So that is how you compute the power factor. Then part C, the distortion factor of the load current, DF, right? So what is DF? That is I1 RMS over IRMS, right? I think that I1 RMS, that is 15 over root 2, IRMS 14, and you get 0.76, right? Hope that's clear. Then part B, the total harmonic distortion of the load current. THD, how do you compute THD? So you can use 267 or 268 or 269, right? So one of those you can use, or even you can use 270 also. Since you know DF, you can easily find THD, right? So we are using one of it, right? So THD is square root of I squared RMS. We have computed that 14 squared minus I1 squared RMS 15 over root 2 squared divided by the same I1 RMS squared, right? So in this case you get THD be 0.86. So we normally denote this as a percentage. So in this case that is 86%. Is 86% good? Anyone? Do you think this is a good system design? Anyone?
Yeah, should be great.
Any other answers? Is THD 86% good?
Yes, good, sir.
No, actually no. THD, if you can remember the discussion, THD has to be as low as possible. You can remember, the higher the THD means, so even the name says total harmonic distortion, no? So THD means it talks about a distortion, no? If that distortion is high, mean that is not good, right? So THD has to be as low as possible for a good system. Then only all those things that I told you about audio system and power systems apply, right? So THD has to be as low as possible for a good system, right? Otherwise, there will be many distortions, right? That will distort the operation of the system, right? Okay. Yeah, the noise is too much. Yes, good. Yeah. Okay. Right. I think we've reached the end of the chapter, right? And we are almost reaching the end of the time also. So yeah, good. So we've reached the time frame, right? So please, I want you to go through, repeat the sums we did, right? No point going through the theories again and again, right? Go through the sums again and again, applying those theories, right? Using the sums, try to understand the theories, right? Within the coming week, please go through everything up to this chapter, chapter 2. Repeat the the exercises, right, and make sure you understood everything and you can work out any sample question related to this, right? In addition to that, if you have any doubts, right, if you have any doubts, don't wait till the next weekend, right? Just send me an email, right, by any means. let me know, right? I can, of course, get back to you, right? As a homework exercise, I have given you some sample questions here, right? I have given you some reference. This is a very useful book, right? This is available in your book collection, right? I think you know how to access your book collection. So this link is given to you in the welcome email, right? So if you go to that particular link, right, you will see all the related material, textbooks, right, in this particular drive, right? So related books are copied here, right? So you can basically download them and use it, right? Please use these related books. For example, now this book is most widely used during this delivery, right? So that is the same book mentioned here as well. Please download this and start using it, right? And I want you to go through these, try these 5 examples at home, right? Please try these 2 examples at home, right? And if you have any doubts working them out, please let me know. These are related to some of the concepts that we discussed so far, some of the concept discussed last week also, right? Please try this, right? And you should be able to apply those theories and work this out, right? Okay, so that is the end of this chapter, right? So I think tomorrow, right? So tomorrow will be the next class at 4:30. So we'll be starting the discussion of the next part of the discussion, right? Any doubts before winding up the session? We are nearing the end of time. If you have any doubts, and we'll be uploading the material, the slideshow. Slideshow is already there. The recording will be uploaded respectively for Triple E and Mechatronics. So Mechatronics, it will be here. For Triple E, it will be here, right? In here and here, right? Please use those material as well. Okay. Drive link. If you can open, so this is the email, no, welcome email sent by Mr. Shanaka. Everything is there, right? If you go down, even
So
the sorry,
how does it get the lecture slides, sir?
lecture sites will be in this. Can you see my screen? In here, you can see this link, right?
Yeah,
Yeah, this is the link.
yeah.
So this is the, are you Triple E or Mechatronics?
Triple E.
Yeah, so for Triple E, this is the place.
Sure.
Right. In addition to that, right, we'll be extensively using these simulation software. For FPC, we'll be using Multisim and Proteus, and of course, MATLAB will be used. Right. So I want you to get these software installed. Right. So the links for those installation packages are given here. For example, if you open the link for Proteus, you can see here there's an exe file, and there's some license file for that using which you can crack it, right? So please get this software installed because we'll be using this. We'll start using this software soon, right? In addition to that, there'll be multisim, right? Use this link. Before start installing this, please download this video. There's a video MP4 file here and watch it. right? There's a description there how to activate your multisim, because without activating this multisim version, you can't use it. The first thing will be you'll have to download this ISO file, extract it to a folder, right? Then watch this video and go through this readme also, right? And see how exactly you can activate this. Without activating, you can't use this multisim software, right? Please get these two software installed, right, as soon as possible, because I'll be not just talking every time, because even, I mean, when I explain something, I will, I tend to use this simulation software to verify any results and show you, okay, that it really works, and this is how it works. Likewise, I want you to get this software installed, right, and be ready, right? Tomorrow or maybe next week, I'll start using this software, right? Please get them installed as well. In addition to that, I'll be using MATLAB also, right, soon. So then, but you see it's huge, no? 12.5 gigs, right? So, but this also you should get installed, right? For multisim and Proteus, it's better you get the same versions installed, because I'll be using the same versions. So I have multisim 13, the same version. So it's better you use the same version as well, right? This software. Then Proteus 8. Yeah, 8.6. So please get them installed. Everything is given to you. The links are there. Go through this email thoroughly, and everything is given here, right? And if you have any doubts, any difficulties, please get back to me, right? Yeah, so in addition to that, yeah, you have a group, right? So you can use that, but of course, don't use it as a social network, right? So this is simply to post information, right? Yeah. Okay. Anything for mechatronics? I think Mr. Abhita has shared you the link, right? Yeah. So this link, so this is for the mechatronics. Let me just post it here. So this is only for mechatronics people, right? If you haven't got it, I think you can use this. I have pasted it on the chat window. Okay, so everything, the slides, the recordings, any material, until you get the Blackboard access, you will get the access, will appear in these drives, right? Yeah, so then everything will be fine. Okay, so anything else? Okay, so what I want to emphasize here is don't wait till the last moment. As I told you, please go through what we completed up to date now within the week before the start of the next session, right? And if you have any doubts, please get back to me. Please repeat everything we did again and again, right? So that you will understand and you will register things in your mind, right? And always please refer to those textbooks, right? Very important that you go through those textbooks, because it's very difficult to cover everything within this limited period of time. So then you should of course do additional referencing, right? So that you can learn many things, right? Okay. So if you don't have any other doubts, we can simply wind up the session. Okay. Okay. Then thank you for joining this session and for the participation, right? So we'll meet tomorrow at 4:30, right? So don't be late, right? We'll be starting at 4:30, right? Stay safe, right? Thank you.